All right, a little physics review for you. Let's talk force and weight. So one thing that's going to be important for us to remember later on in this course, maybe not immediately, but definitely when we talk about energy balances, is going to be Newton's second law. So force is proportional to the product of mass and acceleration. So hopefully in your physics class, you learned that the sum of the forces that act on a system is equal to the mass times the acceleration. And all these little arrows over force and acceleration mean is that it's a vector, right? So it's direction and magnitude. That's not really going to come into play as much in this particular class, but just keep that in mind. Let's flip on over. Normal forces, or natural forces, not normal, because normal is something different. Natural forces have that unit of 1 Newton, which is the same as 1 kilogram per 1 kilogram meter per second squared, right? So that's taking the units of mass right here and multiplying by them by the units of acceleration to get a force. We can also do this in a different set of units. This might be something that you see in future classes, so maybe it's just something to be aware of. 1 gram times a centimeter per second squared is equal to what's called 1 dyne. So that's important. We can also have a pound force. So this is a pound with a little f after it to represent force. And that's going to be equal to 32.174 pounds mass times feet per second squared. So English units are a little bit weird. I try not to use them in class because I'm more interested in you learning the concepts, but this is here and we'll talk about it if we ever need it. So a quick example. What force is used to accelerate a 4 kilogram mass at 9 meters per second squared? We don't have any directions on that force, and we don't have any directions on that acceleration, so a force is simply going to be that 4 kilograms times 9 meters per second squared, which is equal to 36 kilograms times meters per second squared, and we know that a kilogram times meter per second squared is a Newton. So just keep that in mind. That's force. We also have weight of an object. The weight of an object is the force exerted on an object by gravitational acceleration specifically. So that's G that you learned in physics. Hopefully, that's your gravitational constant. So your weight is going to equal to the mass times your gravitational constant. Two numbers here to remember. Gravitational constant in SI units is 9.8066. Many people use 9.81. And that is the same as 32.174 feet per second squared. We normally see 32.2 used commonly. And your weight's not going to change much with your position on Earth's surface. And that's all we're going to say about force and weight at this particular junction. When we get into energy balances, this is going to come back into play quite a bit more.